Second part would be about logistics. And I'm Jaanus. My colleague, young guy here, is Vitalii. And we are talking about logistics. The whole story. So that how the Starship history has went. So that we started building robots. We thought, oh yes, let's do just great robots, so that we don't know what we do with them, but let's make it great robots. And then a few years back, we figured out that, okay, we came into a position where robot is already pretty good, can drive autonomously, we can leave it on the street alone, and so that let's start making business. So that we started talking with various companies, selling our delivery service behind of them. These kind of companies like Wolt, so that okay, if you want to get food, order food from Wolt, and we will bring it with robot. This kind of scenario. But what we figured out was that it does not work because we are second, third in the food chain, and no one cares about us. So that we need to be on charge of everything. So that we need our own relationship with customers. So that we came into the second step. First one is solved. We know how to build robot. We know how to make it better. So that it's a matter of time when we have thousands, millions of them. It's clear. Question was more like, why we need to build them so many, and what's the motivation to build them so many. So that yes, what we made is that we have Starship application so that people can sign up on certain areas where we serve them into our service, so that they have similar offerings like Wolt. If you want to buy food, you can go to the Routeserver to buy groceries. If you want to packages, then you can sign up for a virtual address. Packages arrives to us first, and we will bring it to your home whenever you want to ask robots to come. So that we build up our own demand channel, so that we have direct relationship with the customers. And today, can we generate demand? Yes, that's solved. I would say that now, from now on, it's more like question that, what next? And from here came the question that, okay, we have demand, we have the robots, but we need to come into break even, so that we need to make money of it. So that just revenue, but paying on top of it, that does not make sense. So question is that, can we get into break even? And I can't say today, yes, we are still going toward it, but we know that when it most probably will happen. So that if everything goes well, this summer. If it goes badly, then by the end of this year. So that from that perspective, we know how to economize everything, so that we are in a break even. And from that on, later on, it's already a question of how to take the world over.
So can I have a question?
Yes.
So what do you mean by break even? So it's delivery isn't plus, or the whole enterprise isn't plus?
Break even is that if you take off investment exercises like engineering costs, but we keep all the costs what are related to running robot platform plus robot costs, build robot costs.
So operational and production costs.
Yes. Then break even is related to that. Yeah. Okay. So that we go to the not
so
paying on top of it.
Break even 2, which means plus engineering costs, and then
engineering cost remains, but we know that in like running level, we are in the break even. We can always continue investing or decrease investing. Of course, if we want to build something for the worldwide, then we continue investing.
Okay, thank you.
But the running costs are covered. Yeah. So that is the logistics is a critical moment to come us to the break even, because there's so many challenges how to optimize in optimized way run the whole robot fleet that it needs to be done like smartly, automated way, and there is no way to do it manually. So you can't give just tens of robots to hypervisor, to the person you saw downstairs on the 3rd floor to see on the screen, and him to decide, oh, this delivery goes to that robot, this delivery goes to that robot. So that, we run out of batteries, let's swap the battery. So that human can't handle it anymore. So that the volumes are so big that everything must be automated already. The typical case, what we have, so that we name them sites or service areas. Mustamäe is one example here, but we have many of them, like in Germany, Daimler manufacturing site. In close to London, we have Milton Keynes, there are 2 sites even. Then we have in US, close to DC, university campuses. We have in California, corporate campuses like Intuit campus. So that these are the typical areas, 3 per 3 kilometer. We can make them bigger or they are smaller depending on the case, but these are the sites. And usually these are like 10 to 24 hours open. We have up to 40 robots serving this area. Then we have up to 3,000 customers or registered customers there. We do up to 300 deliveries per day, and during the peak time there might be something like 30 parallel deliveries happening same time. Then we have plenty of partners. By the partners I mean that they are in the campus, university campus as an example. So there are Dunkin' Donuts, Starbucks, and so on, so on. So that, Subway and so on. So that plenty of vendors who like produce the food what we deliver to the students. Then we drive something like 400 kilometers per day with this robot per site, and we need field crew who is on site, so that they are supporting if something breaks, so that robots breaks or batteries needs to be swapped manually, or we need help in some kitchen if our tablet where we manage the kitchen orders that breaks. So that we need field crew who handles these situations, plus operators you saw on the floor 3. And of course we need to handle all the manual and automated battery swaps depending on the site. This is the typical use case. And the process looks nowadays that consumer first downloads the app, installs it, start browsing, and fills in basket if you want to buy something. Then it goes to the chef, the order, if it has been paid, so that to Dunkin' Donuts or similar place, and they start preparing food. And we need to follow what happens, that has it been done, not done, what is delay, and so on. Then if it's ready, then picker takes it from chef and puts into the robot. Sometimes the same chef runs out of the kitchen and puts the robot into the robot the food. It depends on the place really, but and pickers packers are also used in the peak shops like Tesco shop or Selver shop, where when the order comes in and food does not need to be prepared but just picked and put into the robot. We have field crew in the game, so that sometimes before we head to the customer we need to swap the battery or do some other adjustments. Then starts consumer side, so that consumers see that, oh yeah, everything is ready, robot starts coming to me. And you see that there is some minutes left until you receive the package. You had a question?
One question regarding swapping the battery. So you don't really charge the robots, you just swap the battery and charge the battery asynchronously.
Yeah. Yes, there is two concepts. One concept is that I have huge battery in a robot. You put it into the charging station and it takes 12 hours to get the whole battery charged because it's so huge. But during the time when it's in the docking station, robot sits idle and does not do anything. So that this is like consequence. On the other side, it can drive like almost whole day. And second concept is that we have the small batteries, and after each 1 or 2 or 3 deliveries, you just see that, okay, it's empty. It goes to the battery station, swap the battery, and after 5 minutes, if boot and everything is done, it continues with the next deliveries.
Okay.
And it's more flexible. But on the other side, of course, you have complexity related to battery swapping stations.
Yeah, also the operations and that.
Yeah, if it's fully automated, then operators even don't know sometimes that the battery has been swapped in meanwhile.
Okay. Okay. What's average delivery time?
Depends on the length of the delivery. That's one. And second, it depends what you buy. If you buy from Tesco like 2 huge bags of stuff, like 70 items, then picking itself takes maybe already half an hour. So that
several robots come one by one, so it's packed, and then one by one they go into a customer.
yes. Which means that we have maybe onto the previous picture. So that this is the Milton Keynes. We have Coop, we have Tesco, we have robots on the field driving toward the customers. We have pickers, packers here who are dealing with gathering the food from the shop. And so that the robots are either arriving back to the site to pick up right away something what is prepared for them, or they are waiting in idle mode to when someone just orders. It depends on the time, so that sometimes we have low time, sometimes we have high peak time. So, and last piece, of course, that we have control center following the whole process, so that the hypervisor is the one who just supervises that things go smoothly, and then we have operators who just resolve the task by task, and yeah, so that I hope that you saw it downstairs, so that it's somehow clear. So that this is the flow, so that there's plenty of tools what are used, so that we have the customer tool, we have kitchen tool, we have pickers packers tool, we have field crew tool like app, so that they know that, oh, there came in task, I need to go there and swap the battery or do this or do that. Then we have the customer app is already just in this different stage, and here we have internal tools for different control center roles, so that various tools, everything is related to logistics, ETA calculations, and so on, so on. So, so that how much the robot delivery or robot logistics is similar compared to like taxi logistics or the package delivery. So by my investigations, what I have done is that the regular package delivery is the easiest one. And when we tried the cooperation with one of the global logistics company here 1 year back, and we had some data from in-house data from their side, and we just feed it into our system and simulated how effectively we can do it. Then we already figured out that we can beat them. So, and when we figured out that how they handle it, then it's much simpler, because for them mainly it's milk run. I get my 100 packages into van in the morning, and then I just start driving around and just deliver to every place where I feel that the most optimal way it is. I don't care where customer is at home or no, I just ring, you are not at home, okay, you don't get the package, I will call you later or send SMS, so that do it in that way. So that it's pretty simple what they do, and ETA, even if they provide that, yes, we might come to that area where you live 2 o'clock up to 4 o'clock, be at home, so that it's pretty broad range how they optimize it. Yes, they have unknowns from traffic, but it's kind of expectable what happens. We know what happens in certain times. The peak times are also known, that when users usually be at home and so on. Fuel and battery management, purely organized, nothing automated. Support crew, they don't need, because car driver can handle everything what he wants to support his car. With taxi, many similarities, so that it's on demand, more critical. If I compare like Yandex, Taxify, Uber, who is providing me taxi faster? Them. Okay, I will cancel all the rest of the orders. I will do it in that way. So that on demand is more critical, of course. So that the range of the accuracy is should be pretty good, but still you mainly need to react like in half an hour. You don't have luxury to say that, okay, I will come in 2 hours, pick me. So that there is still a different exercise compared to like package deliveries or even to us. And so on, so on. They have some similarities here, but what is maybe specific to robot logistics is that we are also on demand, but sometimes also planned. We are coming also to plan more and more. I mean that we offer to the customer that, hey, we have the package, here are the time slots, which time slots do you want to pick the package? So that we come to that. So that we can schedule the deliveries. The range is that, so we need to be, I mean that we need to think ahead much more, because if in grocery delivery the queue is so long that we can't come right away, there's no free robots, then we need to think ahead many steps that, okay, this robot has delivery, it finishes it after 1 hour, this means that this robot comes back, then we can fit your order to that robot, and that can come, and so on, so there's many steps thinking ahead compared to, and it's different to taxi logistics. Then we have many unknowns, like picking, packing of food. We don't know sometimes. Is it queue time in Selver and picker is just slow on that day, or there's too many items in the basket, or they are too spread in different places. So that there's so many varieties that it can't be always said really precisely what will happen. And same with food preparation. There might be that there's 2 chefs in the shift evening and they will do the pizzas in parallel. There might be that there's just one slow chef today at work. There might be a parallel orders coming in from the physical customers visiting these places. That's making the queue up. So that it's unpredictable sometimes. Statistically, we can come good, but it's still a challenge. And of course, what are surprising things are technical reliability, maybe weather affects us so that we can't drive so fastly, or snow, or sometimes lack of operators if someone gets sick, or robot gets broken, then we have one robot less in fleet, we need to recalculate everything based on that. And the customer choices affect too. So the customers are canceling, they are revising, they're not coming out to visit robots, so that sometimes we wait half an hour until someone comes and picks things from the robot. And these things are unpredictable, and these unknowns are affecting us a lot. Of course, peak times, I would say that a little bit similar to other use cases. Fuel and battery management, on our side, battery management, that must be automated so that we need to decide by our logistics system what needs to be done, when and how and where, so that we don't have person sitting in the robot and deciding, oh, I need a battery, okay, let's switch and go to the gas station or do whatever is needed. So it needs to be automated. Additional complication. And support crew, so that we need to also manage support crew. Who is going where, when, to which robot, in which order, and so on. So that these are the complications which are related to robot logistics, and means that we have nice challenges to solve. Okay, exactly. So that our biggest challenges today are related to how to provide the correct ETA for everyone, not just to customer, but also to the field crew. When happens something, to the picker packer example, when is robot coming? You don't need to start preparation too early. For the chef in the kitchen, again, you don't need to send the order right away. You know that if robot arrives in 1 hour, so that why is to start preparing pizza? It gets cold, you need to throw it away, so that and you need to prepare again this pizza. So that these are the situations we need to take into account, and correct ETA is super critical. And of course the whole automation. So that in the end we have nice technical challenges. And here I give over the speech to Vitalii.
My question as well.
Oh, yeah.
Yes.
Whoops. Yeah. How do I? Okay. Should work. Hi guys. My name is Vitalii. I also want to spend just a few seconds saying thank you to DEVCLUB for organizing these events, and thank you for organizing them consistently over the years. So thank you. So now I'll talk a little bit about tech challenges, but I thought to strike a balance where I will tell about the our architecture in general, but then also narrow down to some specific use cases and challenges that we had and have right now. So let's get going. So the first we will talk about actually the problem of optimizing logistics. Okay, the business people want to optimize logistics, and we as engineers need to implement it. How do we do that? Then we will narrow down to the scalability issues. For example, we will talk about the Routeserver use case. Since in the logistics you need the routes from point A to B, and what can happen if you need 2,000 routes right now in this second. And then problems with improving ETA. And then I think we decided that we don't do demo since you had an office tour and you probably saw the operators. Yeah. So, and because of lack of time. So first, the optimization domain. So Jaanus covered most of that. So we have a hungry customer, right, who orders food. He can either order like from the groceries, or we have vendors like pizza. So for the pizza, you also have to account that pizza can get cold. So you want to optimize that. You deliver the hot pizza. For that, we also have actually thermal bags in the robot, which keeps the warm inside. So you have the robots which have a battery, you have battery switching station, and you have all these different variables in your optimization domain, right? You have a chef, the preparation time of the chef, and you have what we call the runners who run in Selver and pick the foods given the basket, right? And you also want to kind of understand, okay, like if it's this many amounts of items, okay, probably it will take this prep time, but you can also might want to update it in real time based on, for example, if there are 2 runners on the side or 3 runners on the side. And we have, of course, the service area. So just a local area, bounded. So this is like most of my area, which we have delivers every day there.
Are you sure that in 44 minutes pizza is still okay?
Actually, that's a good question. I will get back to that a bit later. So how do we do this optimization, right? So the customer just goes to the basket, he pays, and let's take the very, very first case. You have one robot, one customer. So what do? Well, imagine we have this component or service called Routeserver, which gives you the amount of time robot goes from point A to B. Maybe you account for switching when the battery is swapped. You add those numbers together, you get data. Very easy. And you maybe also add up the preparation time, how much the runner picks the food. Maybe a few other parameters, very easy. Then you have intermediate level. Okay, you have these like 3 robots, maybe 4 customers. This robot finishes the delivery. Maybe he needs to swap the battery, maybe not. Okay, so your if-else logic starts to grow. Rules start to get complicated. And yeah, it gets quite hard. So then you have this what I call torment level. You have like lots of customers, some robots, battery switching stations, for example, and lots of different vendors. Selver here, maybe a pizza place here, another Selver or other place here. Yeah, and many of these, and some of the unknowns, like, okay, weather conditions, something else. What do you do there? How do you optimize that? So let's talk about that. And yeah, exactly. We have like this other complex logistics rules. So we talked about the preparation time. Okay. And this is exactly what you asked, like, how do we optimize so robot arrives early to pizza place so pizza doesn't get cold for the customer? So otherwise, actually, we have a place in California, and it's no joke. It's called Blaze Pizza. They're like artisan. They're doing their pizza like, you know, like in clean code matter, like Robert Martin does the code. And like they throw away pizza if the robot doesn't arrive in 5 minutes. And then we had a complaint like, hey guys, actually, they throw pizzas away because the robot didn't arrive in 10 minutes. So they threw like 2 pizzas away and started preparing the new one. So that's how they operate. So we actually had to optimize for that. And that's a real case which happened like a few weeks ago, and we just optimized for that. So, and when calculating ETA for customer, we also have to take into account unexpected things like rain. I will talk actually about rain in a bit, and it will be a very funny story. And yeah, when do we send robot to swap the battery? For example, because there can be a case that this battery switching station, which is in this pod, has a battery charging, but let's say the battery charged just for 60%, and the bot has the battery which is 30%. Okay, how do you decide? Do you actually finish the delivery and then come back, and you can hope that you can come back, or you die because your battery dies, or you swap for the 60%? So there are all these use cases and edge cases where you kind of have to balance. And first we solved that with just a simple heuristics, then more complex heuristics, so some if-else rules. But then we decided it's not enough. So what do we do? How do we solve all of this? So a little bit about the components. So just to give you the overview of this, how do we solve this problem? So first we need this, we have a Routeserver, which was built by Pavel, the first presenter. It's built in Go, it's super fast. Its sole job is to say, okay, like, not sole, it has like many responsibilities around the Routeserver, but its main use case is like, okay, you have point A, point B, tell me the distance, the estimation, the robot driving there, and if it can be handled autonomously by the robot. And it has some other things. And then imagine in the optimization, probably you need like the matrix of these routes. You need like from point A to point B, sometimes from B to point A, because sometimes actually the route from point B to point A is different than from point A to point B. And there's also a router preference. For example, you can choose the safe route over the fastest route. So the Routeserver can handle all of that. Okay, so let's say it's solved. So we have it covered. And then the interesting part, which probably deserves the talk on its own, but because of the lack of time, I will just quickly skip through that. Not skip, but actually explain in short. But it's a really actually exciting part. So
if you show the code, you can spend hours.
Yes. So like this is the code, right? But just shortened version. So we have the thing called Waveplanner. We also call it Optimiser. So what it does, actually a bit of prehistory. So Ahti Henla, who just gave you a tour, our CDO, he just decided, okay, let's use this genetic algorithm to optimize our logistics. So he treated us as like kind of first a pet project, which he turned into like a pilot project, and then actually now it is in production. What's the main point of this genetic algorithm and how it operates? Basically, the main point of genetic algorithm, at first it gets some random plan. It just like says, okay, you robot A, go to this delivery, swap battery here or something. And then it mutates the parameters. And since like you have this very complex domain, so you kind of mutate all these parameters. Okay, like, is this robot going to this delivery? Or, oh, let's take this robot to this delivery. But then how do you know if you're going in the right direction? You have a cost function. So we actually know, okay, in the end, how much the delivery time took for this, estimated delivery time took for this delivery, and then we optimize for that. So we have a built-in cost function, then we mutate parameters in a smart way, in a sense, but still like mostly random way, but just going into the right direction and just optimizing for that. So that's very shortly. Then we have a part called Orchestrator. All it does is just gathers all this state in the service area and gives it to the Waveplanner optimizer. And then given the output, its job is to apply the plan. So actually making sure that the robot will drive from point A to point B and giving these commands. So how it looks like from this perspective. So for example, the Waveplanner orchestrator, first step it does, it gathers through the resources, right? So it gathers the routes from the Routeserver, it gathers the deliveries, the ongoing, and then it gathers the bots, their battery levels, everything else. It gathers the input, sends to Optimiser. Optimiser is completely stateless. It's like no data source, nothing, just input, output. And then Optimiser gives back this list of events. So the Optimiser kind of operates locally for each service area. So this input and all of this is like per service area. Like, okay, given this service area, what's the optimization plan? So, and it spits out the events for each robot. Okay, for example, like this is a screenshot I took today. Just like, okay, the event is like, okay, robot swap battery for this robot. And this event is gonna last for 3 seconds or something. Then the Waveplanner orchestrator sends a series of events which kind of give a command. Okay, for robot A, drive to server. And the command server, the part, it reads the events, and then its job is to communicate with the robot and give more granular instructions, like, okay, like drive 10 meters here, then turn right, then drive here. And then it's job of the robot actually to drive locally and avoid obstacles and everything else. So now I'll actually narrow down and go to scalability use case with the route server. So you saw from the previous slide that the Waveplanner gathers routes from the route server. So actually, we need to calculate like actually thousands of routes per each service area. If you think about it, like we have a bunch of sites, we have a bunch of customers, we have a bunch of robots, and maybe battery switching stations. And now you need actually the matrix for like each route from another route. So it actually, like this is metrics from our Grafana. So for one service area, we had like 2.5 thousand routes. And given that we expand, it would even grow like to 10,000 routes and more. So what challenges did we have? So this Waveplanner orchestrator that I described, which optimizes the logistics for each service area, it ticks, it's like a cron job which executes every 15 seconds, let's say, for each service area locally. And then we started to see the situation where the tick duration took to be like 20 seconds. And actually for us it's too long, because we have some dynamic events happening now, and we need the logistics planner to always re-evaluate the current state of the world to make the most optimized decisions. So yeah, I started to measure, okay, like where can we have the bottlenecks? And I found two main ones. So one was the gathering service area resources. And we had some bottlenecks when we were interacting with the bot servers. In the end, it turned out that there were some DNS issues, which Martin Picklock from Site Reliability Engineering team solved. So this was solved, fine, done. But then we had another, as you can see, this load correlates with the route matrix request. So what was the problem there? The problem was that we were actually, yeah, this is another graph. Showing that the Routeserver was having a hard time in the evening because we had orders in Milton Keynes, which is area in London. And Milton Keynes is a very complex area where we have many routes. And so yeah, this duration of optimization grew very much. We had stuff broken, Routeserver being overloaded. So that was the problem. So the first, when we first started doing that, we started just like saying, okay, here's the whole matrix. We were sending this whole matrix of 2,500 routes to the route server and saying, hey, compute me. And the route server, don't get me wrong, the route server was very slick piece of code. It's written in Go, very parallelized. Everything was really good. The problem was how we communicated with the route server. So then I started to actually, yeah, this is from my notebook. So I just started to see, okay, maybe some routes are not needed actually. So this is just my notation. The V is actually what we call virtual stop. It's actually with the robot location. The R is recipient. And S is just some site, like Selver. So we found out actually we don't need the routes from robot to robot. We don't need the routes from site to robot, from recipient to robot, and from customer to customer. So a recipient is just like customer location, the pin, like on the Taxify you put. So I just reduced that, like, okay, one commit, because at 8 p.m. our logistics was crashing. And for you to understand, the logistics is now a very core domain in Starship. So when logistics crash, the whole business crashes. So that's how it is. So now logistics is our core domain. So this is what happened after the deploy. And as you can see, of course, I made the change at 8:23 p.m. Yeah, so that was probably a hotfix, right? So yeah, and then we saw a dramatic drop of the routes. So we actually, this was me writing the, yeah, for Milton Keynes reduction was from 2.5K routes to 813. Awesome. So, and in a way, we now kind of relaxed and yeah, we survive. Okay, we kind of, our logistics is ticking gradually. We are kind of doing fine.
I have a question.
Yeah.
Meanwhile, so you basically you don't do tests because actually you know always locations of the sites, number of robots. You don't do simulations in order to predict that kind of situations. Just because it looked to me that you just realized in production, oh, too many robots, too many locations. So
No,
what's the situation?
the thing is that with this, you can't simulate that, but you still need the real routes. Because you have these dynamic routes, you don't know, like you can simulate that the robot will go from point A to point B, but what if the robot stands here in 15 seconds, and then what if it goes to the manual mode, and the operator for some reason decides to take another route, or this route is closed, and actually we have these dynamic situations where the routes are closed, so we also have this upcoming dynamic states. But that's exactly the point that, yeah, I will now tell that how we kind of try to optimize it even further. So yeah, and we kind of went into this situation where these Waveplanner ticks, right? We call them ticks, like one iteration of the logistics plan. So it happened that it was like, okay, at the evening, same time, it was not anymore 20 seconds, but more like 8 seconds, so quite bearable. But we had another problem. We know that we were going to expand largely, and that the main problem actually is that this is the graph I took today just from the Routeserver. And the thing is that you can see that there are like spikes of load. Okay, there are some, this is the get route matrix operation. And you can see that like, okay, like sometimes it responds to 3 seconds, but you can see that the load is actually not evenly distributed. And like we wanted to solve this problem, and I want to explain why it's important to solve this problem. Because imagine that the Routeserver has a given amount of CPU. Okay, one solution is just to scale it up, right? We have Kubernetes, no problem. I just say one word to Martin, or just like change the Kubernetes YAML config and just add more instances, and we pay more money, fine. But then we didn't utilize our resources in a good way, because we had a lot of idle area, right? Like these things, like these gaps, you can imagine, right? Gap here, gap here, gap here, where we could just like utilize the CPU, and it was more or less like idling, right? So now we thought, okay, like how do we solve this problem? How do we make the load of this routes calculation evenly distributed? So we came up with this solution, is that we will split the routes into two categories. One will be what we call the static cache, another dynamic cache. The static cache is where there are routes which don't change like frequently, right? Like server location probably doesn't change very frequently, and then the customer location, right? So there is, let's say, one route from server to customer, but we still need to update it occasionally, maybe even 5 minutes, because let's say the route can be recalculated because, for example, the road is closed, or even like on the pedestrians there are some problems, and our mapping team will kind of detect that and make a change. So there are some occasional updates, and we have to take them into account. And then there is, so let's say we update it every 5 minutes. We could maybe do 10, but then we could have these use cases where what if the route is not available anymore, so let's say 5 minutes. And then we have a dynamic cache, which includes all routes with a robot, because robot is moving and we want always the route from robot to the customer. So we update it often, so the cache policy is updated every 15 seconds. And now if you think about this Waveplanner orchestrator, it gathers the resources. The way it did it before, it kind of, when it ticked, right, it said like to the Routeserver, give me 2,500 rows now. But okay, why? Or like why it needed to calculate it now if then in another 15 seconds it's like idling and doing nothing and then repeating again. So we actually kind of decided to decouple this Routeserver fetching completely kind of from the tick process, and we evenly distribute the fetching of routes over update time. So for example, imagine here in static cache we have 5,000 routes, so we will kind of batch this 5,000 routes into whatever in 5 minutes, then you get like, okay, like you like in 5 seconds you kind of fetch by 100 routes, for example. And then you get them all in the evenly distributed fashion. And then when the tick happens and the Waveplanner says, give me routes, you're just like, here's my routes. They're like taken from the cache. And same from the dynamic cache. And again, because we already have it split and this only updates every 5 minutes, here we have to update every 15 seconds. This will be less routes. So again, less load on Routeserver. So again, it's more distributed load for Routeserver, which means for the same amount of computation power, we can afford to calculate now 10,000 routes, 20,000 routes, even probably more. I should do load testing. So, and yeah, now the rain case. So we have a rain, right? So just rain, nothing would go wrong. But what actually happens? So I call it chain effect of misfortune. So with the rain, we have less autonomy, because the robots don't see obstacles maybe very well, and then the task is created for operators. So more tasks for operators to help our robots. And then there's a queue of robots growing because the rain is happening in the whole service area. So now robot drives slower. Why it drives slower? Because in autonomous mode, well, it just drives forward, but now it needs a help from operator to resolve some task. And when this drives slower, it means the battery dies, because they are more in the idling state. And now when the battery dies, it means that actually the whole fleet of batteries die. So we have like this cemetery, like this zombie robots on the service area, right? Just doing nothing. And now what do? We have field assistants who drive to robots to replace the battery. But actually what's the main effect is that the ETA for customers gets screwed. And we had this case in the George Mason University, just like this or last week, where the rain happened and exactly these things happened. So we haven't solved all of these problems right now. So this is my main point. Like we have many of these, like kind of like building quite unique robotic logistics platform with quite unique challenges, but there are even more challenges. So for example, what do we want to solve in the near future is, okay, let's replay the historical scenarios as I showed on the map, like this different configuration, right, of different resources. But now, okay, let's say we replay, but what if we change some parameters just because we want to see how the algorithm will behave? What if we add more robots into that configuration? Or what if we add more customers? So, and again, then it revolves into simulation. Okay, let's actually simulate that. So if we simulate the load, we can then plan the resources, and thus we can plan the delivery throughput planning. We can know, for example, how many deliveries we can handle given this amount of robots, and what will be the ETA for the customer. So again, we can simulate. And the testing challenges. So currently what we don't do, we do not, given continuous integration, we don't have like this continuous testing against historical logistics data, historical meaning like both older cases and newer cases, continuously. Because like what can happen, the risk is you can have regressions. You can optimize your logistics, you can think everything works well, but then the old cases start to behave somehow differently. So we need to implement that as well. And yeah, I'll just say explicitly, join our team. We're actually, like, the real state is that we are quite under-resourced right now. We are only 2 people in logistics. And logistics became quite a big deal for Starship. So now it's only Kyrie, another developer who's somewhere here, and me, and Jaanus as business. So we're hiring actively, and to be honest, we don't care, like, if you're from Java shop or JVM shop. Internally, we write using Go and Node.js. Node.js was historical. Our monolith was written in Node.js. The newer services like this optimized Routeserver is written in Go. I wrote authentication in-house system in Go. We kind of quite like it. And yeah, we look at your experience, knowledge, and skills to resolve complex problems. And I guess we don't have demo time. So thanks.
Maybe
Questions?
a couple of technical questions.
Couple? We are over time, but.
We're like really,
And I start with one.
yeah, but we have exactly 2 questions. One.
Can you go deeper into genetic algorithms that you use?
Yeah, I can. That's a very good question. So the answer is honestly I can't, and you know why? Because our Octi wrote the algorithm, and that's actually another challenge. The Octi is like what we call.
It's a reverse engineer.
Yeah. No. The Octi now is like a bus factor. I don't know if you heard about this concept, right? Yeah. How many people you need to know to be overridden by bus so that the knowledge is lost, right? So, and now the actually over upcoming quarters, we want to gradually take ownership over the service. While of course Octi will contribute and everything, but we want to take ownership over that service. The main point, what I want to say, currently we have a lot of other challenges to solve. Like optimization is already doing fine, but we have these things like ETA and like the whole orchestration process, etc. But with optimization, so it's written in C++, a genetic algorithm, written by Octi, which we will slowly get ownership over time.
What parameters does it include?
All of this, yeah. For example, like it includes like configuration things like chef preparation time, or like things like okay, how much time it takes for the food to prepare, and all this bot battery level, bots locations, customers locations, some other configurations. For example, different penalty times. Okay, how much do we want the robot? We can, for example, optimize with the example of hot pizza. We can optimize the robot to be there as quickly as possible, even if we know the risk, for example, that the chef might prepare food a little bit longer or something like that.
Does it include time of the day? Like you know that the traffic will go bigger and thus...
Not at the moment, no. No. But yeah, it's a kind of, the cool thing about this optimizer is that the complexity of the domain will grow, and we will need to get more smart with this optimizer. But it's already kind of quite smart by itself, since because of the genetic nature. Like, it just swaps things, and that's why this approach was chosen by Ahti in the first place.
It was first time used for Daimler RoboVan project in Tallinn. So that when we made a pilot project together with Omniva, and we optimized the whole wave so that when we received 50 packages from Omniva in the morning, we sent out a text message to all the customers saying that, hey, choose your time from 1 o'clock until 8 o'clock, up to you. And then each time when a customer made a choice for some slots, we re-optimized right away for the next customer, next slots, for the next customer, next slots. And when everyone agreed, then we had one rough optimized plan. Then we recalculated in 15 minutes, waited, calculating, optimizing a million options, and then it said, okay, I'm ready, let's go, let's do. But this was like milk run planning, this classical way. Now we are doing it more like real time, like after each 15 seconds. Repeat again, optimization, repeat again, optimization with new parameters. Yeah. And outcome is the most cheapest plan that is chosen.
Yeah.
Thank you. And next question, Kirill, please.
So, do I understand correctly that road planning is a totally separate thing compared to ATA estimation? So ATA is
just one component. Your road planning is just one component.
So how you calculate ATA then? So
yeah,
one is genetic, no one understands,
that's
clear.
Yeah.
The second one is ATA, how you do that?
Yeah, so the ETA is completely kind of directly connected to this optimizer, since when the optimizer like gives a plan, right, this genetic algorithm, it kind of, what's the plan like? It knows basically, given its estimation, when the robot, like the last step of the robot in terms of one delivery is that the robot drives to the customer, and the optimizer kind of estimates exactly the time, given all this state, the global state of the service area, when the robot will arrive to the customer. So that's like when we know what's the ETA in the end.
But we can add so that we are decomposed ETA, so that we are going to microservices, so that example, chef preparation times.
It's a separate model.
Separate modular. Yeah. So we just add. We have this kind of orders with this kind of items in the order, so that tell us how long it takes.
Yeah.
It tells and we use it. So that, and we let the data team to reanalyze and optimize based on historical data how to handle the preparation.
And chef preparation time is just one component of optimizer input. So of the genetic algorithm optimizer, it's just like one of the inputs, that we also kind of optimize. So so the preparation time is like separate model. Thanks.
All right. Thank you so much.